remember at the beginning of this chapter, we said that kinetics was concerned with two topics. The first topic was based on rates. And knowing the rates of a reaction, this gives you the rate law. We talked about the integrated rate law. We talked about the method of initial rates in order to help us figure out that rate law. So we've definitely talked about rates of reactions for a good chunk of time now. The second part, and this is actually the first start of that second part, what we're concerned with are the steps of a reaction. Okay, and so that's what we're going to focus on the second half of this chapter. In other words, the part of the question that we're asking here is how? How does a chemical reaction actually proceed? So in order to answer that question, how does a chemical reaction proceed, we've got to introduce a new thing. And it is called a reaction mechanism. So you may have heard from other people that take organic chemistry or other chemistry classes that they talk about something called a reaction mechanism. What a mechanism is that it's a sequence of steps that define the pathway from reactants to products. So a reaction mechanism is a sequence of steps that defines the pathway from reactants to products. Okay. An informal description of what a mechanism is what happens to the atom. So when you get this one mechanism or one molecule reacting with another molecule, how does it happen? And so that's what we want to know. So the simplest step in a mechanism is based on a single collision, and we call that an elementary step. And this is a really simple concept. Each proposed mechanism must be described at this level, or the overall process cannot be described. So in that sense, if every single step or every single thing that happens is part of an elementary step, that means a mechanism is really the sum. If you want to think of it this way, a mechanism is really a sum of the elementary steps. Okay. Now, both experimental data and chemical intuition, or experimental data like the order of the reaction with respect to a reactant, or an intuition like knowing that opposites attract and that acids neutralize bases and stuff like that, they're used to propose mechanisms. And so let's take a look at a mechanism. This is I stole this from another textbook. So you've got a molecule of NO2 colliding with another molecule of NO2, and when this happens, you form a molecule of NO, and then you've got this molecule of NO3. Okay, so it looks like this O, and I'm going to circle it on the first NO2, is transferred to the second nitrogen. Okay, and then once you make that molecule of NO3, then in the second step, you've got carbon monoxide, and it looks like the oxygen from NO3 is transferred over to the carbon, so that's how you form CO2. All right, so this is a great way of looking at a mechanism using a picture. Let's write out what we've got. So in step one, we've got NO2 reacting with NO2, and we form NO and NO3 minus. Okay. And then in the second step, we're taking that NO3 minus and reacting it with carbon monoxide, and we form NO2 and CO2. Okay, and those are our reactions. So those are the two steps. Okay. Now, if I was to add both steps up, okay, let's see what we get. We've got NO2 plus NO2, and then I'm going to add that to the reactants of step 2, So you got NO3 minus and CO. I'm going to add all the products up, so you get NO plus NO3 minus plus NO2 plus CO2. Okay. Now, are there things on the left-hand side and the right-hand side that cancel out? Well, yeah, you've got the NO3 minus because that's shared. Okay. So I'm going to cancel those out because it shows up on the left and the right-hand side. You also have a molecule of NO2 that shows up on the left and the right. So I'm going to cross those out as well. And so what we're left with is the overall reaction. NO2 plus carbon monoxide forms NO plus CO2. And so this, to answer that question, give the overall reaction, that's it. That is it. Now, is there a substance, what substance is involved in the mechanism but is not an overall reactant or product? It's NO3 minus. Now look at this. Now NO3 shows up as a product in step 1, but then we turn around and use it as a reactant in step 2. So there's a special name that we give to substances that we use like that become a product in one step and then a reactant in another. We call those intermediates. Okay. So in the previous mechanism, there were 2 elementary steps. And in general, a mechanism may have 1, 2, or 3, or many more elementary steps. And it's critical that we distinguish between an elementary step and the overall reaction. So let's get some more terminology down. The first word is molecularity. Molecularity refers to the number of atoms or molecules as reactants in an elementary step. Okay. Now, the simplest cases in terms of molecularity, you could have a unimolecular step where you have one reactant. You could, and for an example of that kind of a reaction, is like taking ozone, O3, and ozone breaks apart to form O2, plus you have an oxygen molecule, oxygen atom that's free. And usually ozone is in an excited state. So I'm going to put a star next to that tells us excited. Okay, so that's that. If you have one reactant in the step, that's unimolecular. If you have 2 reactants, we call that bimolecular. So bimolecular, 2 reactants. Okay, so an example that if we were to do the reverse reaction where you have O2 plus an oxygen and that yields to O3 ozone, that would be a bimolecular reaction. Now, the most interesting case is called the termolecular collision, where you have 3 bodies. Okay. The more probable case that happens in a gas is the bimolecular. So you're going to see the bimolecular a lot in reactions. Now, what kind of a process has to occur if it's a termolecular? What this would look like is you've got substrate A, let's say it's a gas, and then you've got another substrate A, but you've also got this metal that's also a gas. And the 3 of them actually combine, you get A2. So the A's combine, and then you get the metal by itself. Okay, now what that metal does, though, what the M does, is that it takes away energy. And allows the 2 A's to combine. All right. So that being said, let's try another mechanism just to get our feet wet, see how this works. So here's an example. A suggested mechanism for the reaction of nitrogen dioxide and molecular fluorine is this. So it's a two-step process. In step one, it's bimolecular because you've got NO and you've got F2, and they combine to form NO2F and then you've got a fluorine by itself. So it looks like one of the fluorines, I'm going to circle one of them, is transferred to the nitrogen. Step two, you take the other NO2 and you take the other fluorine, they combine, and you get NO2F. So the question is, write the chemical equation for the overall reaction and identify any reaction intermediates. Part B, what is the molecularity of each elementary step? Well, we actually talked about molecularity already because, me being a dum-dum, I already said this. If we go back up to step one, you can see that there's two reactants and that they're colliding. So step one is bimolecular. Okay. Step two, same deal, two reactants. It also has to be bimolecular. Okay. So we took care of part B first. All right, now part A. What we want to do is write the overall chemical equation for the overall reaction and then identify any intermediates. Now, one thing we can do before we write the overall step, now that we got these really nice pictures, you do form a fluorine atom by itself at the end of step one, and that fluorine atom is used as a reactant in step two. So there it is. That is your intermediate. So F is your intermediate. So you have one intermediate for this reaction. So then finally, write the overall chemical equation for this overall reaction. Let's do that. So in step one, you had NO2 plus F2 yields NO2F plus F. In step two, you had NO2 plus F yields NO2F. Okay, so what we want to do is add these two together. Now, before we do anything else, does anything cancel out? Well, you do have the fluorine. You do know that the intermediates cancel out. So canceling those two out, that's it. So you're going to have 2 NO2 plus F2 yields 2 NO2F. And so that would be your overall reaction for this reaction. Now that's all well and good, but let's see how this stuff that we're talking about now, how does this connect to all the rate law stuff that we talked about before? So if and only if you are characterizing an elementary reaction, you can directly write the rate law. All right. But if you are characterizing the overall reaction, you cannot directly write the rate law. So what this is saying is if you take an individual step, an individual elementary step, you can write a rate law for that. But if you're trying to write the overall reaction rate law, you can't. All right, so why? Now, if you don't know what's going on at the atomic level, you cannot confidently assume the details of the processes which lead to the order. And so that's why you can't write a rate law for the overall reaction. You can only do it for the individual steps. Now, going back to elementary steps for a minute, the concentration of each reactant in an elementary reaction appears in the rate law with an exponent that's equal to its coefficient in the elementary reaction. So the concentration of each reactant in an elementary reaction appears in the rate law with an exponent that's equal to its coefficient in the elementary reaction. Now, wait a minute. You're probably sitting there going, okay, Jim, wait a minute. Wait 1 minute. Because you said back when we were talking about the method of initial rates that I distinctly said you couldn't assume that. Well, It turns out if we're talking about a rate law for an elementary step, so assuming that the overall reaction has more than one step, okay? If we're talking about an elementary step, then yes, it's true. Now, if we're talking that the reaction is just one step, then we can't assume that. So there is a big difference here. This works. And the exponent is going to be equal to its coefficient in the elementary step. This only works if we're talking about a step that's part of an overall. If the reaction only has one step, we can't do it this way. Okay. So for the uniform unimolecular decomposition of ozone, only one molecule of ozone is required for the reaction. So the rate expression and the rate law would be this, that the rate would be equal to the negative change in the concentration of ozone, O3, divided by the change in time. And so this would be equal to the rate constant K times the concentration of ozone. Okay. Now, what would be its elementary reaction? This. O3, ozone, breaks down to form O2 plus an oxygen. Okay. All right. So now bimolecular reactions are of two types. So that's unimolecular. Bimolecular reactions have two types. Either you're going to have A reacting with B, so you're going to have two different reactants. And so the rate law would be this, that the rate would be equal to the rate constant K times the concentration of A times the concentration of B. Okay. Or you could have reactant A reacting with another reactant A. So you have the same reactants. Okay, and that rate law would be like this. Rate would be equal to the rate constant K times the concentration of A squared. Okay, now this functionality can actually be realized if we take a look at the image that's down below. Okay, so let's take a look at, we're supposed to get some information from this picture. So let's take a look at what we got. So here's our first picture. Okay, and so all these red molecules, we refer to them as B. Okay, and so what we're looking at is the frequency of A-B collisions involve any one A molecule. So the blue ball right here is proportional to the concentration of B molecules. So you've got, in this case, you've got one A and you've got many Bs. Okay, and so that means that the collision frequency is going to be proportional to the concentration of B because there's so many B molecules. Now, what if we double the concentration of A? So in this situation in part B, you've got two A's and still many B's. In this case, the concentration, the collision frequency is still going to be pretty much like that of the concentration of B because there's still so many B's to only two A molecules. Okay, now if we keep doubling the concentration of B, so in this case in part C, what if we double the concentration of B? We only have one A molecule. So you got one A, and then you're doubling the concentration of B, so that means you're going to be doubling the collisions between A and B. Because there's so many B's now, A can't move around without hitting one of them. Now, if I double the concentration of A, okay, and I double the concentration of B, what we see is that we get 4 times the collisions. And so this is kind of the rationale behind why I made that statement earlier that that each reactant in an elementary reaction appears in the rate law. The concentration of each reactant appears in the rate law with an exponent that's equal to its coefficient in the elementary reaction. And so that's why it all kind of this kind of makes sense of that statement. All right. So putting it all together, this table over yonder basically talks about all the three types of molecularity reactions. You've got the unimolecular, you've got the bimolecular, and you've got the termolecular reactions. Okay. Now, we didn't really talk about the termolecular reactions at all, and that's because we're going to stay away from them, because that means that if we're getting into third order reactions. Okay, so we're going to stay away from third order reactions in this course and just keep it to the first, second, and 0th order reaction. All right, so let's take a look at another example. So the example I want to take a look at is actually the first one that we talked about when we looked at the rates, when we looked at mechanisms. So we're going to talk about this one right over here. So you got NO2 plus NO2 reacting to form NO plus NO3 minus, and then the NO3 reacts with CO to give you NO2 plus CO2. So putting this all together, I'm going to rewrite what we had previously. So you have this, that NO2 plus NO2 yields NO plus NO3. And that NO3 plus CO yield NO2 plus CO2. And we added those up. We were able to cancel out the NO3. We canceled out one of the NO2s. So we had NO2 plus CO yields NO plus CO2 as the overall. Okay. Now it turns out, like looking at this reaction, think about this for a minute. Is there a reaction that's slow, or is there a step that actually slows up this reaction? It turns out, yes, there is. Everything in this reaction hinges on us preparing or making NO3, because if we can't make NO3, step 2 can't happen. Step 2 only happens if we make NO3. So in this sense, we call step 1, because that's the critical step, we call this the rate determining step, or RDS. Okay, and RDS again is rate determining step. The rate determining step is all hinging on us preparing or making something. In this case, step 2 can't happen if we don't make NO3. So step 1 is our rate determining step. If step 1 goes fast, then that means step 2 can happen faster. If it takes us a long time to make NO3, so if step 1 takes a really long time, that's going to limit how fast this reaction can go. So based on what we're seeing for the rate laws, for step 1, the rate would be equal to the rate constant K times the concentration of NO2. Now, since we're dealing with the first step, there's 2 NO2s, so that would be squared. So we know that this is a second order step. Okay, and because there's 2 reactions, it's bimolecular. For the second rate law, for the second step, it's going to be equal to the rate constant K times the concentration of NO3 times the concentration of CO. All right, so which reaction is the slower one? Well, we talked about this, number 1, because it's hinging on making NO3. And because we're trying to make that intermediate, step 1's got to be the slower step. So which molecule is most important for determining the rate? It's going to be NO3. That's the one that's going to that's going to hold everything up. So what do you predict is going to be the overall rate of the reaction? Everything is going to be hinging on the concentration of NO2. everything is going to be hinging, the rate of the overall reaction is really dependent on the the concentration of NO2. So in this case, if we try to predict the overall reaction, we could say pretty good, with a pretty good overview, that the rate would be equal to the rate constant K times the concentration of NO2 squared, because step 1 is our rate determining step. Now let me ask another question. Which concentration has no effect on this rate? So out of these, NO2, NO3, and CO, which one has no effect? CO. Doesn't matter what CO does. It's in step 2. Everything that's hinging on step 2 is NO3. If we can't make that, step 2 is not going to happen. So everything's hinging on step 1. And so to summarize kind of how we deal with kinetics, the way that we deal with kinetics problems is using this flow chart right here. What we try to do is determine the rate law by experiment. Once we've got that, we then try to come up with a mechanism for the reaction. And then we try to predict the overall rate law for the mechanism. Okay. Now, if the predicted and the experimental rate law doesn't agree, that means our mechanism's wrong and we got to try again. And so we try to devise a mechanism and then predict the rate law based on what we've got. So a lot of times this part right here, it's a circle. We just keep going around and around until we refine our model. Now, once the predicted rate law and the experimental rate law agree, then we also look for additional supporting evidence to make sure that we've got the correct mechanism and the correct rate law. And so that's pretty much a really fast overview of what a reaction mechanism is and what kinds of things we ascertain out of it. Now, if you go on in chemistry and especially organic chemistry, you will study how these mechanisms are put together, and there's actually patterns to the mechanisms. There's a whole lot of information that you can get out of it. But this is going to give you a little bit to whet your appetite until then.